And cue the theme music.
Live from Southern Illinois University, Edwardsville, it's time for CMIS468, Business Telecommunications.
That's right. Welcome back to an online edition of Chapter 6. And so let's get started. We're going to do all of Chapter 6 in this video because we lost one session due to snow, and we're going to lose another session due to the in-class lab. So Monday we're going to make cables together. It just doesn't leave us any time in class to talk about the first chapter on Wi-Fi technology. There'll be another chapter on Wi-Fi later on in the textbook. That'll be on exam 3. And I do have a review sheet out on Blackboard already for you, so just heads up that you've got exam number 2 coming up on March 2nd, so get ready. As we transition from talking about wired solutions to wireless solutions, it's important to look at the differences. Wireless is a fundamentally different beast than wired is. Having a huge background in cabling myself, I'm biased. A wired connection is always better than a wireless connection. Always, always, always. That's just me, but hopefully I can convince you of the wisdom of this. You should already be comfortable with the idea that there are two different fundamental types of antenna for any wireless connectivity, because you probably have used them both, and we use them both for different wireless applications. So the first is an omnidirectional antenna. So certainly every Wi-Fi access point is typically omnidirectional, versus a dish antenna, which is unidirectional. It's to stream a signal from point A to point B in more or less a straight line. So normally I do this exercise in class, but everybody should be comfortable with the antenna. This is a wireless device. It's not Wi-Fi because it's not 802.11, but this sends a wireless signal to unlock your car. So if you're like me and you can't remember where you parked, and you're doing that to try to find your car, but you're not close enough, there is a way to turn this, which is in fact an omnidirectional antenna, into a unidirectional or dish antenna. I don't know if anybody's ever tried this before, but this is science. If you put it under your jaw like this and then use your mouth, you can actually create a dish antenna with your head. Some people do it like this on the side of their head, but I think that looks ridiculous. This looks okay. And just do that. Get the signal. So if you're try this when you go out to the parking lot. Get far enough away from your car that it doesn't get the signal with an omnidirectional antenna, and then do this, and you'll be amazed how far away you can be. And still, now you have to kind of play with the shape of your mouth to get it to stream in the right direction, but play with it. True fact. Just like with the car, your wireless signal never goes as far as you want it to go, whether you're talking about Wi-Fi or finding your car, or really any wireless signal. This is a fundamental problem. Wireless transmission has many, many more propagation problems than a wired connection does. A wired connection only has to deal with one propagation problem, which is basic attenuation. It's linear. The longer you go, the signal starts off big and then gets weaker and weaker over distance in a linear fashion. Not so with wireless, and also the other problem is we have a lot more sources of electromagnetic interference, and we'll talk about some of those. When we're talking about wireless transmission, we use the term shadow zone to indicate a dead spot. You and I just call it a dead spot, where signal isn't going to reach. Some place in the building, or even someplace outside, but typically where signal is blocked by something. This could be something stupid like the type of paint that people use to paint the walls can sometimes block signal, or an obstacle, a metal wall. Please note that the higher a frequency you're using, the worse, the more of a problem shadow zones are going to be for you. I mentioned that wireless propagation, actually attenuation, is a much bigger problem with wireless than it is with a wired connection. That's because of this inverse square law attenuation. So I mentioned before, With a wired connection, it's linear and gets weaker and weaker. With wireless, it's a lot worse. It's an inverse square. So as soon as the attenuation of the signal gets a little weaker, and then it drops off dramatically. So it doesn't go slowly over distance. You're close, and then wham, all of a sudden you don't have any signal. That's a result of the inverse square law. Even if you're not a big math person, you should still kind of understand how if you have the distance is being squared in the denominator instead of the numerator, things are going to get much worse very, very quickly. And of course, signal does spread out in a sphere, not a circle. It's in 3 dimensions with an omnidirectional antenna. Inverse square attenuation is problem number 1. Problem number 2 is absorptive attenuation. So there are different things that can absorb signal and degrade signal. Air is one, water is another, people are another. People absorb signal. In fact, we're absorbing signal all the time. We don't think it is a health problem at this point, hopefully. In fact, if we crammed enough people into the classroom, we could probably start affecting Wi-Fi signal. But it'd take an awful lot of people to absorb that much signal. It'd be an interesting science experiment. In order to explain a lot of these attenuation issues, we have to talk about frequency. And in order to talk about frequency, we have to go back to high school science class and talk about the frequency spectrum. So the electromagnetic spectrum, this is not in the book, but I kind of pulled this out to make sure everybody's comfortable with the idea that the frequency spectrum starts at 0 hertz. A hertz is just a cycle, and goes up to infinity and beyond in terms of the frequency count. So you have, visible light is kind of right here in the middle. Radio waves, where that we care about in terms of everything that we transmit from an IT point of view is a radio wave, with the possible exception of microwaves, all the way up to gamma rays if you're going to turn into the Incredible Hulk here. The entire spectrum is divided up into sections called bands, service bands, and we use these service bands for different types of service. TV is one, FM radio is another, GPS is another, cellular telephone is another. They use different frequencies. Why? So we're not broadcasting on top of each other. We have to keep these types of communication separate in order for them to work. So in the U.S. we've chopped it up a certain way. In Europe they've chopped it up a different way. Just FYI, it's not the same everywhere in the world. Each service band is further subdivided into channels. So you're already familiar with, on a television station, think of it, you probably have never even seen an old-fashioned TV where you have to change the channel. You're changing the frequency in order to receive at the frequency at which the television station is broadcasting. Same thing with radio. When you change the channel, change the station on your radio in your car, you're changing the frequency. So it starts at 108 on the right-hand side and goes down to 88.7. Every band is chopped up into channels, and Wi-Fi is no different. We really care about 2 bands when we're talking about Wi-Fi. One is in the 2.4 gigahertz range, and the other's in the newer 5 gigahertz range. There are others we'll talk about, but these are the 2 test-worthy ranges. Notice that these are unlicensed bands. The reason these are unlicensed is, well, if they were licensed, like with a radio station, has to be licensed. Because you don't want other people broadcasting on 88.7 when your radio station has a license to be on 88.7. Whereas it would be a big pain in the butt if you had to get permission from the FCC every time you wanted to set up a new transmitter, i.e. an access point. Every time you wanted to set up a wireless router. I hate using that term, but just for simplicity right now. Every time you wanted to set up a wireless router, you would have to get permission if you wanted to, every time you turned it on, anytime you moved it, if you changed the geographic region where you were transmitting signal, you would need a license. Well, that's no good for Wi-Fi because we move this stuff around all the time. Therefore, it's in an unlicensed band, which has its own problems. Just as an example, one problem would be in your own neighborhood, if you're broadcasting Wi-Fi on Channel 6 and your neighbor is broadcasting Wi-Fi also on Channel 6, you're going to interfere with each other's signals. And because you can't take them to court, you're not licensed, they're not licensed, you have to figure it out yourself. One of you has to change your channel in order to get a clean signal. Like I said, each service band is chopped up into channels. Wi-Fi is chopped up into channels. Now, depending on what Wi-Fi protocol you're using, you're going to use, you'll have a different number of channels available to you. The Wi-Fi protocol we care about is 802.11 for all Wi-Fi devices. Please remember the 802 number for Ethernet. I don't know if you remember off the top of your head, 802.3. So 802.3 is wired Ethernet. 802.11 is for Wi-Fi connections. And there's a standard numbering system, although it doesn't make a lot of sense until you just get used to it. And since we know the most important thing about telecom is understanding the layers, hopefully you're asking yourself, but Tim, what layer are we talking about? Well, the answer is, the physical layer covers twisted pair and fiber optic cable. So we're using Wi-Fi instead, so we know it's layer 1, but it's also part of layer 2, the part of layer 2 that handles MAC addresses. So 1 and part of 2, that's what layer Wi-Fi works at. So Wi-Fi, at its simplest, you need 2 devices to set up a wireless network. One is an access point. And here's an Aruba one, here's Cisco, Linksys, another Cisco. Some have antennas, some have antennas built in. This is item number 1 from our 2 things. Item number 1. Item number 2 is a wireless network card. Note that they're incredibly small. So this is just a USB wireless card. It's ridiculously small. In fact, the only reason it even needs to be this big is for the connector into your USB port. But typically a wireless network card is just a chip with an antenna. And if you were to open up your laptop inside the lid, I don't recommend doing this. However, if you looked inside the lid of your laptop, you'd see this wire going up the length of the laptop lid. So the act of lifting up the lid raises the antenna on your laptop. Isn't that cool? Now that we understand what protocol we're dealing with, 802.11, any of the flavors of 802.11 that we're going to talk about, cover just the radio transmission on this side, the transmission from the access point to the wireless network card. Let's say it's on a notebook, on a tablet, on a smartphone, whatever it is. But please note that the access point itself has got to have a wired connection itself. It is plugged back into a switch. In fact, I really think it's a good idea to think of access points as wireless switches, just because they work at part of layer 2, and they're in part performing that function of passing frames back and forth on the network. So the access point is actually doing some conversion here. When it transmitted information, it has to understand 802.11 on one side, but it also has to understand 802.3 on the other side. So there are 2 protocols that the access point has to deal with. This is just a reminder that 802.11 uses unlicensed radio bands, which means we can move our access points around and move our laptops around, which is a good thing. And I mentioned already why there's a downside to being in the unlicensed band, that you have to negotiate with other network owners to make sure you're not interfering with each other. You may not cause unreasonable interference. This is interesting. If you're wondering how you could cause unreasonable interference, if you're wanting to cause some mayhem, you can, on certain access points, boost the signal. And if you're doing it at the same channel as your neighbor, that would effectively jam their signal. Don't do this. This is rude. But I'll tell you how later.